Hello everyone, and welcome to our first lab in the energy unit. Up till now, we've done a lot of work with the law of conservation of energy. We've counted boxes of energy, we've broken pies up into pieces of energy, right? But we haven't really dealt with any numbers yet. We don't have any math models to actually be able to calculate an amount of ability to produce change, right? Which we're calling energy. So we're going to start this out with looking at elastic potential energy eventually. And in particular, we're going to look at the elastic potential energy stored in a stretched or compressed ideal spring. Why is it ideal? We'll talk about that as we go. Okay? But we're not going to worry about like other elastic things here, rubber bands, bungee cords, things like that, unless they act like ideal springs. It's pretty much where we confine ourselves at this point. So, as you of course would know, right, you have to stretch or compress a spring in order to store any elastic potential energy. It doesn't have any ability to produce change unless it's stretched or compressed. Now, why does it have that stored elastic potential energy when you stretch it or compress it? Because it tends to pull back to its original shape, right? It exerts a force, right, when it's stretched or compressed. And so that's one of the variables we're going to look at, because before we can actually develop a math model for elastic potential energy, we kind of need to understand how ideal springs actually work, right? So we're going to do a little lab here on springs. One of our variables is the force exerted by a spring. Notice the symbols we're going to use: F with a subscript of S, S, of course, for spring. Right? We're not going to use an E like we do with EE for elastic, because this isn't really talking about elastic in general. It's specific to springs, right? So this is the force exerted by a spring. And then the other variable, as we talked about here, is how much it is stretched or compressed, right, is going to affect this. So one little thing here is that we tend to use a little more complex term sometimes instead of stretched, right? There's a term called elongation, or how much the spring is elongated. Note the symbol is an X. Now, we've used X before for horizontal position. Why does it get used here again? Well, I think it's because you're changing the position of the end of the spring, right? Whether you're compressing it or elongating it, stretching it, right? You are changing the position of where the end of that spring is. So, an X, I guess. Plus, we've already used E for other things, right? So, the question, though, is what exactly do I mean by elongation? And this is important when it comes to how you're going to do your lab, okay? So here's a spring, just kind of hanging up. You're going to have these in the back of the room to look at and to measure things with, okay? But right now, this spring that's just hanging there, does it have any elastic potential energy? No, right? It doesn't really have any ability to produce change because it's not stretched or compressed. So what we're going to do in the lab is we're going to hang masses from the spring, like that. Right? We've got these little plastic mass hangers on which we can pile different amounts of mass, and that will cause the spring to stretch. Now, when we're measuring elongation here, we have to be careful about what do we mean by elongation, right? And note, it is not the length of the spring. Because here, the spring has a length, but it's not exerting any force, and it doesn't have any elastic potential energy stored. Right? So we don't want the length of the spring, we want how much it is stretched or compressed. For example, on my diagram, that would be this. Right? I might want to measure from here, say, to here. Now, that doesn't mean that when you go to do the lab, you can't measure the length of the spring and subtract, right? You can do it that way. There's several different ways you can set this up, and I'm not going to tell you exactly how, right? But you've got a meter stick, you've got a spring, you've got a bunch of masses. That's all you got in this lab. So however you want to set that up, but just be sure that when you're measuring and recording the elongation of the spring, it's how much it stretches, not the length of the spring. Okay, you got to be very careful there. And when we're doing concept builders and things, you got to be very careful about what he's asking about. Okay? So these are our two variables that we're going to check and how they are related to one another. So here's our purpose: to create graphical and mathematical representations of the relationship between the force exerted by an ideal spring and its elongation. So elongation, we're just going to measure with a meter stick. By the way, you'll see on your lab sheet, I would like that in meters, so please convert to meters. Okay? If you don't, your slope will be weird, it'll be off, and the Google form won't take it, so make sure you're converting to meters. But what about the force exerted by the ideal spring? Well, let's do a quick little force diagram here for the mass hanger and the masses in this case, right? So I'm just going to get rid of the spring, and we're just going to do a force diagram on this. So what forces act on this? Well, of course, gravity acting down. And what else? Well, something's holding it up, right? Something's keeping it from falling. Is it a normal force? Yeah, not really, because normal forces are surfaces supporting something, like when you set something on the table or the floor. In this case, it's not being supported by a surface. It's being supported by the spring. Right? So the spring force would act upward, right? Right? And this will pull down on the spring, and so the spring will pull up, right, on the mass. Little Newton's third law idea there, right? Interaction. And how big will this have to be? Well, of course, they will have to be balanced. And they're balanced because we're not going to have these springs bouncing around. Please do not do that. I don't want you to destroy the springs, right? They're just going to be at rest. You'll put the masses on, you'll put it at rest, then you can measure things. And of course, we know how to measure the force of gravity, or calculate it, I should say. Our old friend, as long as we're near the surface of the Earth, m times g, where m is the mass that we're hanging, and g is our local gravitational field strength, our old friend 9.8 newtons per kilogram. Right? That means that our mass is going to have to be in kilograms. It starts out in grams, you're going to have to convert. A lot of conversions in this lab. Okay, you'll see that again in the data table. So we can basically calculate the force exerted by the spring from this clever little way we have the lab set up, right, by calculating how much weight we're hanging from the spring. Okay. Now, one key thing here, although the mass hanger is made out of plastic, so it's very low mass, it still does have mass. And that would be enough to throw off the lab because we're not using a lot of masses in this case. So the mass hanger says right on it, it's written right on the side, it is 5 grams, which, 3 decimal places to switch to kilograms, right, 1,000, is 0.005 kilograms. If you look on your lab sheet, you will notice that all of the masses you are hanging end in 5, and that's because of the mass hanger. Right, so you can add the masses. So for example, the first one you're going to do is 25 grams, or 0.025 kilograms. So you'll basically just add a 20 plus the mass hanger, that'll be your 25 grams. With me there? Now, these springs, when you get back there, they're little springs, okay, and they are very sensitive springs. And if you've ever played with actual springs before, especially little ones, or like slinkies, or things like that, if you know that slinky toy, you know that if you like stretch it out too much, or kink it, or something like that, it's going to break and it won't go back to its original shape, right? And then we've essentially destroyed the spring. So we need to be careful with these, okay? I have other springs that are much stronger, that are harder to destroy, but for this lab, I really needed things to be sensitive, so we're using these little weak springs, okay? So please, don't take anybody else's masses. You should have just the amount you need on your table. Don't overextend them. Don't pull down on it and let it bounce up and down and those kinds of things, because you'll destroy the spring, right? One of our little goals here today is that we're going to try to do the lab without destroying any springs. That would be a good thing, okay? One other little thing I want to talk about, and it talks about this on the lab sheet, right, is how we're going to make the graph. I'm very explicit on the lab sheet here, but when it gets time to graph our two variables, which one are we actually controlling here? The force exerted by the spring or the elongation? Yeah, we're controlling the force exerted by the spring by controlling the force of gravity by controlling how much mass we put on, right? So that makes this one the independent variable, and then we're measuring how much elongation we have. Could we do the lab the other way? Yeah, but it would be really hard, right? Like, we could say, okay, how much mass do we have to pile on here to make it stretch a certain amount? Yeah, that would get tedious and very long. So it is much easier to do the lab this way with this equipment, right? That we control how much force the spring exerts, and then we measure the elongation. However, when it comes time to graph, and you'll see this again on your lab sheet, I want you to flip the axes around because I want the slope to mean a particular thing, okay? So I want you to graph force exerted by a spring versus elongation. So this will be on the vertical axis, elongation on the horizontal. So a little bit of a violation of our rule of thumb, our convention, if you will, on which variable goes on which axis. But again, that's because I want the slope to mean something particular, which you'll see when you do the lab.